Hi, I'm William Stevers, and I'm going to be showing you in this first part of the video basically the hardware components of our design and how it meets all of the challenge requirements at a hardware level. Shown here is the block diagram, so if you want I would pause the video just so you can kind of see the components before I show them in the next part. Alright, so starting at the receiver, there's the SDR in black, it's the HAC RF1, and then that's directly connected to the LNA, which is plugged into the power combiner, which is the center of our system with the adding interferometer. So each part of the power combiner is connected to one of the RF switches. Here's the first RF switch that basically allows you to switch between the wide and narrow baselines. The second RF switch on this side is connected to a 50 ohm termination and the reference antenna, which is used for both baselines. And this is the circuit that controls the RF switches with -5 and 5 volt logic. And this is the isolated supply for the LNA. Flipping the system over, we see our two antennas, the reference antenna and the narrow antenna, which share a ground plane. And then over here we have the wide baseline antenna. Finally, here's the power circuitry that is connected to a 9 volt source, either a battery or a bench supply. With the system powered on, we have this green LED, and then typically you'd be holding it like a periscope, as I was at the very beginning, but we're just going to keep it this way for the sake of convenience. And now we can demonstrate switching the relays. So basically here we can switch between the 50 ohm load and antenna 3, just like that, and you can see the relays changing there in the inset. And then, this is used for switching to the single antenna mode. And then on the other side, we can switch between the narrow and the wide baseline. But typically, we'd leave the right side on antenna 3. That way, we can take our baseline measurements. So here, I've actually rotated the antenna bar thanks to the T-extrusion, and we can see how we kind of actually take measurements. So basically, the compass up here with the levels, so we can make sure that the compass is free-floating with the levels. And this allows us to get a heading that is then later used to actually take interferometric measurements. And that is the entire hardware overview of the final system.
Hi, I'm Anton Schlegel, and I will be talking about how we are going to find the
transmitter.
Right now we have GQRX open, and we are going to show a demonstration of when the transmitter comes on. And as you can see right there, the transmitter came on, so that means that's where it is. And so once we find the frequency where the signal is coming from, we will next be moving into Q spectrum analyzer to actually take metrics.
Anton is basically just defining broadside in terms of a compass reading, so we're going to see that it's actually 60 degrees for this example. And then I will basically be setting the things in the GUI, so we're at 5.802 gigahertz, so we're going to pick the middle one, and we see the simulated data just like that. Now, there's Q spectrum analyzer, and so we're going to zoom in at our peak and just start recording data. And then the blue plot is the average power, in relative dB. And so we begin to plot them in the direction finding plot below. And now here's Anton.
Now I define broadside and relative to the compass heading, and in this example 60 degrees. After finding broadside, we then start taking measurements with the system in 10-degree increments. This process continues until we have enough measurements to match the shape of the calibration data.
Now we can see that the shape here is kind of similar in a lot of ways. And looking up at the calibration data, so first we notice that the initial points from 60 to 100 are kind of flat, and then there's a nice drop off. This kind of makes sense if we're talking about the top range of the calibration data. The process will then continue with the wide baseline to get a more accurate result. So you can see that the simulation works fine, but then we're going to use our guess of 0 to 30 degrees to actually look at the relevant data. We would switch to the wide baseline to take more data to then populate this graph. And we would just take the data in 2-degree increments to get a very fine resolution estimate.
On figure 1, I have my received signal from the SDR. I have 2 cycles of it, and this is captured through GNU radio. And then on figure 2, I have my generated sinusoid in MATLAB, and I have zero padded the signal to make it of equal length, the received and the generated. Then on figure 3, I have my delay spread profile, which I am cross-correlating the generated signal with the received signal, and I get a spread profile. The delays are not accurate as it depends on where you cut the phase, incoming phase of the received signal. So, but we get the spreading, the delay spread profile characteristics of the channel. And then on figure 4, I have my log plot, and it shows a flat fading.